So out of curiosity, I mean, you guys are clearly a biased sample of the class because you're here and the other people are not here. And so your behavior might not be representative of theirs, at least with regard to this. But how many of you guys find the webcast useful? Do you go back and look at them again? Anybody? Really? Okay. Cool. And it's I mean, obviously it's valuable or you wouldn't keep doing it, I suppose. So you're finding it's useful review? Or is it just on those days that you don't come in that you, yeah? Okay, we were talking about, we're starting to talk about sampling. We talked about parameters and statistics, and I want to talk a little bit about why anybody would want to sample instead of taking a complete census of a population. It can save time and money. You can get a very accurate answer if you do it right. There are situations where you're basically forced to sample, though, for a variety of reasons. For instance, if you're doing destructive testing, you know, you're a company, you make light bulbs. You want to know, on average, how long your light bulbs last so that you can offer a warranty, right? You can't run all your light bulbs until they burn out to figure out what the average lifetime of your light bulbs are. You wouldn't have any left to sell, right? So destructive testing, when the kind of evaluation you do ends up destroying the thing that you're trying to do it to, you're kind of stuck with using a sample. There are actually many situations where you can get a more accurate answer based on a sample than you can trying to do a census of the whole population. And where that can happen in particular is if you have to train people to collect the data or something like that, then you can have a higher level of training for a smaller number of people that can result in collecting more accurate data, where somehow your ability to collect accurate data is resource limited as well. And so you can, by allowing some statistical uncertainty coming from the fact that you're taking a random sample, you can end up decreasing the uncertainty in individual measurements because you can make those measurements either using better trained personnel, using a more expensive, more accurate instrument, making your observation over a longer period of time, something like that. So there's situations where you can actually get a more accurate estimate based on a sample than you can based on a population. In order for that to work, in order for that to be true, you have to draw your sample in a particular way. You have to use random sampling. You have to use probability sampling. And we're going to talk about some of the ways in which things go wrong if you don't use a probability sample. All right, so I want to talk a little bit about the Haidt report on women in love. And this discussion is largely stolen from a book by Xiaomont Wang, came out in 1993, called Sense and Nonsense of Statistical Inference, Controversy, Misuse, and Subtlety. Sheer Haidt, she did a study in the 1980s. She sent out over 100,000 questionnaires to ask women how they feel about their relationships with men. And the findings were reported in a book called Women in Love. She came up with results that were they contrasted very strongly with what the previous wisdom had been, with what other studies had found. So in particular, Kinsey's study from 1953 was the definitive work on sexuality in the United States up at that time. And the Kinsey report found that 26% of women had extramarital affairs. In contrast, Haidt, some years later, but I guess it's 30 years later, 34 years later, found that 70% of women married women had extramarital affairs. Okay, just a huge difference. Now, Haidt claims that Kinsey was wrong because of how Kinsey did his surveys. That the problem was that Kinsey was using face-to-face interviews, whereas Haidt was allowing people to fill out questionnaires anonymously in some sense. And so her feeling was that people were reporting more accurately what their behavior actually was, whereas face-to-face they'd be embarrassed to admit what they were up to. So Haidt argued that Kinsey's figures were biased downwards. Haidt found a quote-unquote flood of unhappiness in the responses that she received. But what makes this kind of curious is that there were other studies that were done roughly at the same time as Height's. There was a Red Book survey, and there was a random sample survey of 2,000 people done by Patterson and Kim, and they both found that roughly 31% of women had extramarital affairs. Okay, so 31% is a lot, is somewhat bigger than the 26% that Kinsey had found in the 50s, but a whole lot smaller than 70%, which was the contemporaneous estimate by Height. So Height also claimed that this feminists have raised a cry against the many injustices of marriage, exploitation of women financially, physically, sexually, and emotionally. This outcry has been just and accurate. Okay? But again, a poll from roughly the same time, a Harris poll of 3,000 people, found that family life gives great satisfaction to both men and women, and 89% of the respondents said that their relationship was satisfying. Okay, so again, we have this tension between Height on the one hand saying it's a mess, and other people saying, well, not that big a mess. So what's going on, right? So all of these results are based on sample surveys. Some used face-to-face interviews or telephone interviews. Some used questionnaires. We talked about the difference between parameters and statistics. So the percentage of women in 1991 who had extramarital affairs is a parameter, right? That's some property of the population. We don't get to know the parameter. We only get to try to estimate the parameter based on a statistic, which is what fraction in some sample of women said that they had extramarital affairs. So we've got two steps removed. One is it's a sample instead of the population, and the other is there's a reporting issue. It's what people say about themselves, which might or might not accurately reflect what they actually did. Height was very focused on the issue that what they said was likely to be more truthful if they said it anonymously through a questionnaire than if what they said either face-to-face or over the telephone to somebody who was talking to them. All right, so Height says that her study was representative of what was going on largely because the demographics of her respondents match the demographics of the country really, really well. So let's look at that. So here is we've got this is looking at income, and 19% of the women who responded to her survey made less than $2,000 a year, whereas in the U.S. at large at that time the percentage was about 18.3. Income between 2,000 and 4,000, 12 versus 13. If you look at all of these numbers, they match remarkably well. There's kind of a gap here. I'm not sure what's going on there. I should check that, make sure that's not a typo on my part. But the demographics, the income distribution matches the U.S. population really, really well. Similarly, if you look at where they live, so you look at people who were urban dwellers, 60% versus 62, rural, 27 versus 26, small town, right? The demographics match really well. Look at what part of the country they were from. Again, Northeast, all of these things match remarkably well. Look at their ethnicity and race. Again, the demographics match remarkably well in each of these slices, each of these strata, each of these slices through the culture, through our society. So, does that mean that Height is right? The fact that the demographics of her group match the demographics of the country, does that mean that the reported behavior of her group matches the behavior of the country? Okay, and the answer is not necessarily, right? There are other explanations, and we're going to talk about them. And the biggest thing that comes up in this particular survey is non-response. So who is likely to send back a questionnaire who receives it? Somebody who is single, unhappy, has a lot of time on their hands, so forth and so on, or somebody who is happily married, busy with family and kids, so forth and so on, has other things to do, right? I mean, it's just, the people you would expect to return the survey, you would expect them to be disproportionately people who were angry and had time on their hands, right? Anger is a much stronger motivator than happiness. You don't see big demonstrations out on the street, hundreds of thousands of people saying, we're happy, everything's great, right? I mean, people go out to complain about what they don't like, right? About what they're unhappy about. Okay, so it would be, it's certainly the case that people might be inhibited about answering truthfully and answering face-to-face versus answering anonymously in a questionnaire. And that's some amount of that is probably going on. But what I think the larger effect is that's going on here is simply selection bias. It's who chose to respond, non-response bias. So let's talk about that. So Haidt sent out 100,000 questionnaires. She only got 4,500 back. Okay? So the level of non-response, so the number of people who didn't return the questionnaire divided by the number of questionnaires she sent out, is 95,500 divided by 100,000. This many didn't come back. So her non-response is 95.5%. Okay? Now, if she wants to claim that the results of her survey match what things would be for the population at large, she needs to believe that the 95.5% who didn't respond would have responded the same way the 4.5% who responded did. That their answers would have been similar mix of things. Now, we've given one reason that that is unlikely to be the case. That is, who's motivated to respond, who has time to respond, who spends their time that way. It's more likely to be people who are unhappy and angry and whatever than people who are satisfied. Yes?
Isn't it unlikely if there was a non-response bias for those responses to come back matching so closely to the demographics of the country?
Okay, so the question is, isn't it unlikely for the demographics of the sample to match the demographics of the population so well if there was non-response bias? And for my eye or for my ear, what I think that that's actually saying is that misery and unhappiness don't obey economic and demographic boundaries, that they're spread kind of uniformly across the country, that you're not, rather than saying that the opinions of these people match the opinions of the other 95.5%. I think it's more likely that the people who are unhappy in all walks of life. So, but I have no data to confirm that, right? That's just another hypothesis that explains the same observations. Okay. All right. So we could ask, well, what could have happened if these other 95.5% of people had actually responded? Well, suppose that her estimate was that 70% of women had extramarital affairs. Okay, what would have happened if the other 95.5% of people had responded? Well, suppose that they had all reported that they had extramarital affairs, right? If that were the case, then the estimate that she would have gotten based on what she did get and what she was missing would have been that 98.7% of women had extramarital affairs. Okay? Well, what if none of the women who didn't return their questionnaires had reported that they had extramarital affairs? Well, in that case, this 70% would have been 70% of 4.5% would have been mixed with 0% of 95.5%, and the estimate would have been 3.2%. Okay, so depending on how those other 95.5% of women might have responded, the estimated rate of extramarital affairs could have been anything from 3.2% to 98.7%. Right? Her estimate that it's 70% is completely riding on the assumption that those 95.5% would have responded the same way that the 4.5% did, who did respond. Does this make sense to everybody? Okay, so we can, non-response introduces a bias. We don't know how big that bias is, but we can put a bound on the bias. The effect of that bias could have decreased the estimate down to 3.2 or brought the estimate up to 98.7. Is there a question? Yeah.
Instead of
If you multiply it by 70%, you get 70% out. That's essentially what she did. She pretended that everybody who didn't respond would have responded the same way that those who did respond. So she got 70%. Yeah, because if you take 70% times 4.5 plus 70% times 95.5 divided by 100, it's 70%. Okay, so that's in essence the assumption that she made. Okay, all right, so you get the idea that we don't really know what the story is for the non-responders. We don't really have a reason to believe that they would have responded the same way the people who did responded. If we assume that they did, then non-response doesn't introduce a bias, but we don't really have a justification for that. And depending on how the non-responders would have responded, the estimate could have been washed enormously in one direction or the other. Okay. All right. In general, when you are making a sample survey, taking a sample survey, there are a variety of things that can introduce bias. Non-response is one of them, but there are a number of others. So one of the most important is frame bias. So the frame, so typically there's a population. You're wanting to learn something about the population, but you can't really draw a sample from the population because you don't have like a list that has everybody in the population on it. So you don't have a way to sort of ensure that you could pick anybody you wanted. Instead, instead what you typically have is a frame which tries to match the population as closely as possible, but won't match it exactly. So for instance, if I were trying to, well, here's an example. In 1936, Literary Digest took a poll of 10 million people trying to predict the outcome of the presidential election. Alf Landon was running against Roosevelt. The prediction based on their sample was that Landon would win by a margin of more than 2 to 1. Okay. Instead, Roosevelt won. And what was going on? Well, what was their frame? They weren't able to sort of draw a sample of people from the population as a whole. They made a list of people and drew a sample from that list. What was their list of people? Well, they were using phone directories, so you had to have a phone number, or you had to be a subscriber to Literary Digest. Okay. Well, it turned out that their list of telephones were still pretty expensive back then. Not everybody had one. You tended to be wealthier than average if you had one. Similarly, to subscribe to Literary Digest, you tended to be wealthier. You tended to be Republican. Okay, so their frame, the sort of set of units, the set of people from whom they were drawing their sample, was not representative of the population. So if your frame, if the list that you're drawing your sample from doesn't represent the population as a whole, then the sample is not going to have a very good chance of representing the population as a whole. Okay, so that's an issue, a case of frame bias. So it happens, this kind of thing happens a lot. There's a list of things from which you can draw your sample, and that list does not exactly match the population. Now, it might be that that mismatch doesn't matter, and it might be that that mismatch matters a lot. The closer the frame matches the population, the less the issue of frame bias. Okay, now, if you're talking to human beings, so that issue of frame bias comes up whether you're talking, no matter what kind of sampling you're talking about. It comes up for survey sampling where you're trying to solicit individuals' opinions, so forth. It also comes up for sampling widgets coming off the assembly line. If the frame doesn't match the population, you have an issue of frame bias. Question wording comes up when you're talking about people or talking to people. And here, it's just very clear that you can get any answer you want by asking a question that's worded appropriately. So imagine the difference in responses you would get to the question, should a woman have control over her own body, including a reproductive system? And should a doctor be allowed to murder unborn children who can't defend themselves? Right? Those are two questions asking for people's opinion about abortion, but they're going to get answers at a very different rate. Right? They frame things differently. Not in this sense of framing question. Okay. Does this make sense to everybody? Okay, so you can really monkey around with that, and people do. People do to manipulate public opinion by taking opinion polls that say, this fraction of people support abortion, and if they had asked a different question, they would have gotten a different answer, even if the content was, about abortion, for the sake of argument. Okay, sensitive topics. You ask people questions about sensitive topics. You might not get a truthful answer, right? I mean, as like An example that's given in How to Lie with Statistics is, how often do you bathe? Right? If you bathe once a week, you might not answer that way. If you bathe 4 times a day, you might not answer that way, right? You could be embarrassed by the truth one way or the other. Okay, similarly, if you're asking people about their use of illegal drugs, do they pay their income taxes or cheat? I mean, there are lots of things where people might not answer truthfully. Now, there are techniques for trying to get around this, like randomized response. There, the idea is the following. You have the person, it's something like this. So, question 1, toss a coin. If the coin lands heads, answer whether you've ever had an extramarital affair. If the coin lands tails, answer whether you're male or female. Right? So the idea there is that the person answering the survey knows that the person who's analyzing the results will not know which question they were answering. And so they will answer, they have anonymity built in because of the coin toss. Okay? But if I know that I administered the survey to 50% men and 50% women, I can undo sort of the expected number of responses to the second question, answering whether you're male or female. So I can somehow statistically subtract out the number of yeses or nos that would have been contributed by the coin landing tails, right? And then use what's left over to figure out what fraction of people reported that they had extramarital affairs. Does this make sense? Okay, all right. So there are ways of trying to get around the sensitivity issue. All right, interviewer bias. Interviewers can bias the results in a variety of ways. If the interviewer has any discretion over whom to pick, whom to have in the sample, then you might pick people who are just sort of look more appealing, look more open, don't look angry, don't look like they're going to stab you if you stop them in the street to ask them a question. I mean, whatever it is. There's also a well-known effect that the interviewee, once you stop to talk to somebody, they're very likely to want to please the interviewer in some way, to say kind of what they think the person wants to hear. It's not even a conscious thing. It's not like a deliberate misstatement of the truth, but it just sort of, it does affect responses. In the book How to Lie with Statistics by Huff, there are lots of great examples of this. I would encourage people to read that if they haven't read it already. How many of you picked up a copy of How to Lie with Statistics? Almost nobody. It's like, it's this thick, it's like $10, and it's fabulous. I really, really, really recommend it. Okay. Let's see. All right, so questions about this before we go on? Okay. We're now going to have a taxonomy of sample designs. There are lots and lots and lots of different ways you can draw a sample. We're going to talk about some of the main ways and then some ways that they can be blended into hybrid ways of drawing a sample. And, if you want to try to keep your eye on the ball, here's the two big divisions are this. Is it a probability sample, or is there some random element being deliberately injected into the selection of the sample, or not? Is it a non-probability sample? That's a huge divide. If it's a probability sample, there are ways of kind of dealing with it to get error bars out the end and figure out what happened. If it's not a probability sample, all bets are off. You have no idea what relationship the results from the sample bear to what the results would have been for the whole population, unless the sample is so big that it basically gives you everybody in the population. If it's almost a census, then you can figure out what might have gone wrong. But if it's far from a census, if the sample is only a small fraction of the population and that sample wasn't drawn at random, you just can't say anything. You can't say anything reliably. You can't quantify the extent to which your answer is likely to be off. All right, so that's the big divide: probability sample, non-probability sample. Among probability samples, then we start thinking about things like, well, in this way of drawing the sample, was every unit in the population equally likely to be selected, or were some units more likely to be selected than others? If some units were more likely to be selected than others, then that raises the issue of bias. And we need to make sure that we take that into account in coming up with our estimates out the other end. Okay, so the terminology here, we have a population of units. Units are the elements of the population. Units could be people, units could be something else. We typically can't draw directly from the population. We're drawing from a frame. We don't have an exhaustive list of everybody in the population. Instead, the list that we have, the sort of the things that we're drawing from are the sampling frame. All right, if the value of the parameter for the frame is different from the value of the parameter for the population, that's going to introduce bias no matter what we do. All right, we're going to talk about little n is going to be the sample size, big N is going to be the number of units in the frame from which we're drawing the sample. All right, so I could draw a sample of people from this room by picking individuals, right? I could say you, 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 you. Okay, that's a way of drawing a sample of individual units. Okay. Alternatively, I could draw a cluster sample where instead of taking an individual, I take a group of individuals. I could say, okay, everybody in the fourth row, you're the sample. Okay, so that's a cluster. I'm picking a cluster is everyone sitting in a given row. Does that make sense? Okay, so if the ultimate thing that I'm pulling is the unit that I'm interested in, it's not a cluster sample. If the thing that I pull is a collection, one draw gives me a group of people, that's a cluster. Okay, a cluster sample. Okay, stratified sampling. So what it means to stratify a population is to divide it into a bunch of non-overlapping groups that are a partition of the population, or in this case, a partition of the frame. So we could think of the class as being stratified by year. So we could divide everyone in the class into freshmen, sophomores, juniors, and seniors. Those would be the four strata. And then I could separately draw a sample of freshmen, a sample of sophomores, a sample of juniors, and a sample of seniors. That would be a stratified sample. Does that make sense? Okay, divide into subgroups, draw a sample from each subgroup. Okay. Cluster sample that sounds almost the same is I divide people into freshmen, sophomores, juniors, and seniors, and then I let my sample be, okay, everybody who's a freshman, you're my sample. That's a cluster sample. Okay? So get the difference? In one case, I'm sampling from the stratum. In the other case, I'm treating that group, as a cluster, and taking it as a whole. Okay. All right, multistage sampling. This happens a lot when we're in things like economic surveys and whatnot. It happens as part of checking the census for coverage, for undercount. So if I wanted to draw a sample of people in the US, I don't have an exhaustive list of everybody who lives in the country. Nobody has a list like that. Okay? The IRS probably comes closest, but all right, so how could I do that? Well, I could do it in stages. I could start by making a list of states. Okay. Then I could pick 2 states from the 50. I can make a list of the counties in those states. That wouldn't be very hard. It's easy to make a list of the 50 states, yes? If I pick 2 states, it's not that hard to make a list of the counties in those 2 states. Okay? If I pull 2 counties from each of those states, in each county, I can probably make a list of the blocks, the residential blocks in those counties. That wouldn't be that hard. Then I could select 3 blocks from the counties, and now if I'm just down to blocks, it wouldn't be that hard to make a list of all the houses, all the dwellings that there are on those blocks, right? And then I could pick housing units at random from the blocks, make a list of everybody who lived in those housing units, okay? So you pick my address, who lives in my house, make a list of them, and then pick one of those people, one of the people who lives at that house. So that would be a multi-stage way of drawing a sample of people. And the idea would be that at the end, you're drawing individual people, but you've done this in such a way that you don't need a list of everybody in the country to do it. So this is a convenience to make it possible to do that. Now, this is multi-stage. If I'd taken at this last step, instead of taking one person from each of the household units, if I took everybody who lived there, that would be a multi-stage cluster sample, because at the last stage, I'm pulling a cluster of people. That make sense? Okay, if I made a list of states, and then in each state I selected 2 counties, and then in those so forth, then I would have a stratified sample, right? Because I'm treating the states as strata. I'm drawing a sample separately from each of them. Okay, if I made a list of all the states and took 2 counties from each of the states, and then at the end took everybody who lived in the household that I selected, I would then have a multi-stage stratified cluster sample. Okay, so you can cobble these things together into all kinds of Baroque structures. All right. So far, so good? This is all fairly plain language stuff, I think. Okay, now how you actually decide which 2 of the 50 states to take, which counties in those states to take, which block, so forth, that matters. That matters a lot, and it really controls the reliability of the sample that you get, the ability to extrapolate from the sample to the population reliably, and your ability to assess the uncertainty in the result that you get. So a convenience sample is not a good way to do it. This is kind of what happened in the Height report. Here it's you take whatever's convenient. So here an example is given here. I mean, suppose I want to know what fraction of the Berkeley faculty are registered Republicans. Okay, I could just start in the faculty phone directory and take the first 100 names and call them. Right? That's a sample of convenience. There's no reason that those first 100 should be representative of all faculty. You know, especially if your last name says something about your ethnicity and possibly about your political affiliation, then that would not be a very good way to do it. I might go to the faculty club at lunch and interview the first 100 faculty who agree to talk to me. Okay, well, who belongs to the faculty club? You think that that's a representative sample of faculty? I don't know, might be. I doubt it, but you know, anyway, okay. So those are both convenience samples. The problem is that you have no idea how representative your sample is once you get it. And you have no way to sort of quantify the error that you're likely to make in extrapolating from that sample to the whole. All right, quota samples are sort of saying, okay, I'm going to deliberately match the demographics of my sample or some features of my sample to some features of the population that I know. So in the Height report, she didn't deliberately set out to have her sample end up matching on those demographic things. So it's not really a quota sample, but it's kind of like a quota sample. So if you sort of say, okay, this fraction of the student body is female, so I want to make sure that my sample has that fraction of women. This fraction of the student body are freshmen, I want to make sure my sample has this fraction of freshmen. This fraction of students are on financial aid, I want to make sure that my sample has this fraction of students on financial aid. I can match on a bunch of characteristics of the population. The problem is that matching on those characteristics which you know about doesn't ensure that the sample matches the population on the thing that you don't know about, which is the reason you're carrying out the survey in the first place. Okay? It could well be that even that some parameter differs enormously between groups that have the same demographic characteristics, and so doing quotas is not a good way to ensure the accuracy of the result. Right. Systematic samples. Here, this is what a lot of people think of when they think of sampling. So the image is that you have a file drawer, and you have 1,000 files in the drawer. I want to end up with 100 files in my sample. So what do? I take the first and the 10th, sorry, the first and the 11th, the 21st and the 31st, et cetera. So I take like every 10th file out of the drawer. And that gives me 100 files that are fairly spread out among the 1,000. Okay? Seems like a reasonable thing to do. There are situations where it works pretty well, but there are situations where it doesn't work that well. And in particular, you can't really figure out whether you're in a situation where it works well or where it doesn't unless you either know the results for everybody or you have a random sample to compare it to. So systematic samples, one of the advantages they have is that they don't really leave latitude for the data collector to kind of pick and choose individuals that seem, there's less room for deliberately introducing bias or having little subjective things come up. But the order of the list, where you're taking every kth element of the list, will matter. And if that order has some association with the property you're trying to learn something about, then you're going to get bias. Okay. Probability samples are the gold standard. This is what we're looking for. Probability samples are drawn using some random mechanism to deliberately introduce randomness. And the analogy is like, look, I'll give you 3 or 4 analogies. So one is you're playing cards. You're playing high-stakes poker. Okay? There's a deck of cards on the desk. You would probably not just walk up to that deck of cards and start dealing a hand of cards and in some high-stakes game. You would insist on shuffling the cards first, right? Okay? Even though you don't know what order the cards are in, They might have been shuffled. They might not have been shuffled. They might be in their original sorted order. Who knows what they are. You want to deliberately introduce randomness so that the result ends up being fair, right? What's our notion of fair? The cards were shuffled well before you dealt the hand, right? Every 5-card hand was equally likely to come up. Okay, so that's taking a random sample is like shuffling the cards. What's another example? Suppose you want to know whether a pot of soup has the right amount of salt in it. Okay? You want to stir the soup before you taste it. Because if you don't stir the soup, there could be a whole bunch of salt sitting in a puddle on the bottom that hadn't gotten mixed in well, right? If you stir the soup well, you can tell from a teaspoon whether it's about right, too salty, or needs salt, right? It doesn't take a lot. And for that matter, if you stir the soup well, it could be a little pot of soup, it could be a cauldron of soup, it could be the entire Pacific Ocean, right? If it's stirred well, 1 teaspoon will give you a very good idea of how salty it is. If it's not stirred well, then a gallon won't tell you very much, right? It just sort of, okay, so stirring it really matters. Same idea, like making a batch of cookies, chocolate chip cookies. Are there enough chocolate chips in the cookies? Is it about right? Well, if you haven't stirred the batter really well, the chips could all be clumped together somewhere, right? If you want to know that your sample, the dough that you get in one cookie is representative of the batch of dough, you need to stir stuff up. So that's what random sampling does. It ensures that stuff is stirred up. Okay. So not only do probability samples stir stuff up so that what you get tends to be more representative of the whole, but if you do it right, when you're done, because we have some idea how random sampling, how drawing tickets from a box of numbered tickets behaves, we can quantify how far off the answer is likely to be from the truth. So remember when we were talking about a simple random sample from a box of numbered tickets. So you pull a bunch of tickets without replacement out of the box. What's the expected value of the sample mean? It's the mean of the numbers in the box, right? So what does that mean? On average, if we did it over and over again, our sample mean would be equal to the population mean. On average. It's never going to it might never match it exactly, but if we average the results of a bunch of trials, we're going to get answers that sort of oscillate. If this is the true population mean, then sometimes our sample mean is going to be over here, sometimes it's going to be here, right? We're going to be off in the typical case, but on average, we're going to be, the average of a bunch of repetitions would give us the right answer. But moreover, what else do we know about the sample mean? We know it's standard error. What's the standard error of the sample mean? So it's the SD of the box divided by the square root of the sample size. Okay? So what does that mean? Well, it means that a big chunk of the time, our sample mean is going to be within a few standard errors of the true population mean. Sort of for most samples, most of the time that we do this, our estimate is going to be pretty close to the truth. Occasionally, we might get an answer out there. But we know from Chebyshev's inequality, if nothing else, that we're not going to be 5 standard errors away from the expected value very often. Not more than 1 over 5 squared of the time, not more than 4% of the time, 1/25th, right? But so if we're drawing our sample at random, we know that sort of on average, we'll get the right answer. And moreover, that typically we can say how far we're likely to be from the right answer. And if we wanted to get closer to the right answer, we can increase the sample size. That would decrease the standard error and say, oh, now there's a big chance that instead of being within this distance of the truth, we're within some smaller distance of the truth. We can control that through the sample size. Now, if we're taking a sample of convenience, if we're taking a quota sample, if we're taking something like that, we have no idea what's going on here. Our estimate could have any relationship whatsoever to the truth, and we can't quantify what's the chance that the estimate is going to be within this distance of the truth, or within that distance of the truth, or something else. Because there's no such thing as a standard error for a sample that isn't random, right? That you need randomness. We have to be talking about a random variable. Okay? So deliberately introducing randomness lets us quantify the uncertainty when we're done in a way that we can't do for other sampling designs. All right. Not every probability sample gives you an unbiased result. We do know that if you take a simple random sample or a random sample with replacement, then the sample mean, the expected value of the sample mean is the population mean, right? So we know that. So way to say that, another way to say that is that the sample mean is an unbiased estimate of the population mean in that circumstance. So the bias is the difference between the value of the parameter you're trying to estimate, that is the population mean, and the value of your, and your estimator, in this case, the sample mean. So on average, the difference between those is 0 if you're using a simple random sample or a random sample with replacement. We're going to talk about that a lot more in the next chapter. But not every probability sample is like that. Sometimes you sample with different items with different probabilities, and there are reasons for doing that. We can talk about that later. All right, so simple random sample is the canonical method. What is that? We've talked about it already. It's a random sample without replacement. It's drawn in such a way that if we're taking little n units from a population of big N units, a simple random sample is one that's drawn in such a way that every subset of size little n of the n objects in the population is equally likely to be the result. So how many such subsets are there? There are this many possible subsets of size little n drawn from a collection of big N, right? Okay. Simple random sample, one way of defining it is it's a sample drawn in such a way that every single one of those subsets is equally likely to be the result, equally likely to be what you get. So that's like you got the box of numbered tickets, you stir them up really well, you grab 5, you pull them out. That's a sample. You need more than 5 in the box. We're drawing a simple random sample. But okay, all right. Okay, that's not how they're typically drawn in practice. This talks a little bit about how people tend to do it. Typically, the way that you draw a simple random sample is to assign a random number to every element of the population and then sort of sort them and take the little n of them that had the largest random numbers associated with them or that had the smallest random numbers associated with them or something like that. We're not going to worry too much in this class about the difference between random and pseudo-random. Computers don't really generate random numbers. They generate pseudo-random numbers. So there's actually some algorithm that produces them. If you know the seed, you know the whole sequence of random numbers. They're not really random, but we're not going to worry about that here. If you're doing elaborate simulations, it can matter. Okay, systematic random samples. So remember we mentioned systematic samples before. It's like you take the first file in the drawer and then the k plus first and then the 2k plus first, like taking every 10th file, something like that. Well, systematic random samples are a variant of that where instead of starting with the first file, you start with one picked at random. And then you take every 10th file after that. Does this make sense? So you start with a random one between 1 and 9. And then starting with that, you then take every 10th file. Okay. So that is a probability sample, right? Every unit has a known chance of ending up in the sample, but not every subset has the same chance of being the sample when you're done. Okay, so here's an example of drawing a systematic random sample of size 10 from a population of 100 things. So you would randomly pick the starting point between 1 and 10. And then if the number that comes up is 1, your sample would be the first unit, the 11th unit, the 21st unit, and so on. If the random number that comes up is 10, then your sample would be the 10th unit, the 20th, et cetera, on up to the 100th. Okay? So if you look at this sort of list, every possible value is in here once. Every possible unit is in here exactly once. And if this row gets pulled, unit 1 gets pulled. So unit 1 gets pulled with probability 10% because there's a 10% chance that this is the row. There's a 10% chance that this is the row. In this case, number 8 gets pulled, number 18 gets pulled, et cetera. So there's a 10% chance that any given unit is in the population, is in the sample. Every unit has the same chance of being in the sample. But what's the probability that the sample consists of the units 2, 7, 23, et cetera? 0, right? Because if it has 2 in it, it's not going to have 7. This one has 7, this one has 2, right? You can't get them both in the same sample. So there are only 10 possible samples in this systematic random sample. There are 100 choose 10 possible samples if you're doing simple random sampling. Okay, much, much, much bigger number of possible samples. You can actually think of systematic random sampling as a random cluster sample. I've divided things into 10 clusters. One cluster is the units 1, 11, 21, 31, et cetera. And I'm going to, at random, pick one of those 10 clusters, and my sample is going to be that. Okay? Does this make sense? Okay. All right. So this is random. Everything has the same probability of being the sample, but it is not a simple random sample, and you need special techniques for dealing with the uncertainty if you do things this way. All right. So let's talk about some of these ideas. So suppose you want to estimate the average size of classes at Berkeley, undergraduate classes at Berkeley this semester, and we're going to think about 7 different approaches. So one is take a random sample of 100 courses from the course schedule, average the enrollments of those classes. Okay? What kind of sample is that? Is it some kind of probability sample? Or a sample of convenience? We're taking a random sample. It's a probability sample. What's the sampling frame there? The courses in the catalog, in the schedule of classes? Does the frame match the population? Sorry? For that semester? Every course is listed in the course catalog, right? I mean, it's listed in the course schedule, right? And there aren't any things listed that aren't courses, right? So that the frame matches the population there. There's not an issue of frame bias. That make sense to everybody? Okay. We're taking a random sample of size 100 from the population that we're interested in. That's just a simple random sample. Right? That's somehow an easy way, clean way to do it. All right. What if you take a random sample of 50 students who are enrolled in the current semester and make a list of the courses that they're each taking and average those lists? Average that list. Sorry? Multistage, cluster, some. Okay, so what's the frame there? Does every course have a chance of being selected or not? Let's assume that every student has the same chance of being selected, that this is a nice simple random sample of students. Some classes have more students. Okay. Okay. So that's very, very important. Let's first ask, though, whether every class is even represented, right? Does the frame match? Does the set of courses that we can get include every course that's offered or not? No? Yes? Okay, so if you have a class with no students, and it's actually in the course schedule, that 0 is not going to end up getting averaged in, okay? But that's kind of like not having a class at all. So I think we have a little technical point here to worry about, but let's assume that if the course has an enrollment of 0, it gets struck from the list, okay? All right, so now we get to the issue of, does every class have the same chance of being included? And that's where your comment matters. If you take a class that has 700 students enrolled in it, and take a seminar class that has 5 students enrolled in it. If we think of a box of tickets, where the tickets are the students in this case, right? A student is representing classes, yes? Then how many tickets go in this box for the class that had 700 students in it? 700. How many tickets go in the box for the class that had 5 students in it? 5. Okay, so we're much more likely to pull the larger class than the smaller class if we do our sampling this way. What's that going to tend to do to the sample mean that we get if we start averaging the class sizes on this list? Is it going to be an unbiased estimate of the average class size or a biased estimate of the average class size? Bias. Okay, is it going to tend to be too big or tend to be too small? Too big, right? Okay, we're going to get the big classes represented more often. So if you think about the difference between asking, do I ask this later? Yeah, okay. So yeah, the difference between, if you ask 50 instructors how big the classes are that they're teaching versus asking 50 students how big the classes are that they're taking, you're going to get a wildly different answer, right? Assuming that every class has one instructor. You know, some have more than one. But if you put instructors in the box, you've got one ticket for each class. If you have students in the box, you have a lot of students for the bigger classes and very few tickets for the smaller classes. Does that make sense? So it's going to bias the results. Okay, so this is a random cluster sample because if we pick a student, we pick all the classes that student is taking, right? So what we're picking is a cluster of classes. Does that make sense? Okay. And it's going to tend to be biased as an estimate of the average class size because we're going to more students representing the larger classes. All right, here you take a random sample of 50 instructors, neglecting courses that are team taught by more than one instructor. You have one ticket in the box per class, right? So this is really this is still a cluster sample of courses because some instructors teach more than one course, right? But it's going to be give you an unbiased estimate of the size of the classes. That make sense? Okay. All right. Separate random samples of 5 courses from each department. Average the sizes of the courses in those samples. What kind of sample is that? We're starting by dividing the course catalog into departments, and we're sampling separately from the department. So each department represents a stratum, right? We've stratified. Okay, we're ignoring cross-listed courses for the moment. Okay, so we've divided the courses into strata, and now in each stratum, we're drawing a simple random sample. Okay, is the average that I get, is every course equally likely to be in the sample? Got head shakes. Okay, so what goes wrong? Why is it? Yeah. Okay, so some departments could have larger classes, but why does that introduce? The question right now is every class equally likely to be in the sample? And that you're onto something, but that's not quite there. Another, yeah. Okay, some departments offer more courses. Okay, yes.
Some departments offer more lower division courses that have more students, so that
Okay, so there's 2 ideas that are kind of they're related, but they're not quite the same. So what she said, if you have a class in a department that offers a lot of classes, right? You have a department that has 30 courses, and you take 5 of those. Each of the courses offered by that department is less likely to be in the sample than if you have a department that only offers 5 courses, because every single one of those 5 is going to be in the sample. Does that make sense? So if a course that's offered in a department that doesn't offer very many courses has a bigger chance of being selected than a course in a department that offers a lot of courses. because you're only taking 5 of however many there are. Okay? Now, if it happens that there is an equal probability of selection, right? Courses don't have the same probability of being selected. Now, if it happens that, as you said, that the department that offers a lot of lower division courses offers a lot of courses, then you're going to get a downward bias in the estimate because you're going to take too few of the big courses because you're only taking 5 of them, whereas in another department that offers only seminar courses, you're going to get all 5 of those nice small seminar courses. Okay, so that's going to introduce bias into the estimate. The reason that you get the bias in the estimate, though, is that not every course is equally likely to be picked. Does that make sense? Okay. All right. Yeah.
So if you're picking 5, unless one department has 4 courses, why would that be a problem? It would only be a problem if one department has 4 courses, right?
No, it's a problem if let's look at a department that has 10 classes. Okay, so here's one that has 10, and here's one that has 50. Okay, here's blah 101. Okay, that's one of the classes in this department, and here's qua 101. Okay, this is this department. What's the chance that this class ends up in the sample? Okay, it's 5 out of 10. It's 50-50 chance, right? What's the chance that this ends up in the sample? 1 out of 10, right? You're taking 5 of these 50 in this department, so this class only has a 5 out of 50 chance of ending up in the sample, a 1 in 10 chance. But here you're taking 5 out of 10, so this class has a 50% chance of ending up in the sample. Okay, so the probability that a course is selected depends on which department it's in if the departments have different number of classes. Does that make sense? Okay. All right, and then if this department that offers 50 courses has a disproportionate number of large classes, right? They offer a lot of large lower division classes, then your estimate based on the sample mean is going to be biased downwards because you aren't getting a proportionate number of those classes. So to get rid of this bias, what you would need to do is you do something like decide on a sampling fraction f, which says I'm going to take 10% of the classes in each department. Okay, so then every class would have the same chance of being selected. Okay, if I take so for this class here, I'm going to take 1 class. You're going to take 5, et cetera. Then I'd have the same probability of selecting every class. Of course, that's not going to work out perfectly because not every department has a multiple of 10 classes offered. So, but that's the idea. So, if you have a stratified sample and your sampling fraction varies across strata, so you're not taking the same fraction of items from each stratum, then your probabilities are going to vary. Your sampling probabilities will vary across strata, and not every item has the same chance of ending up in the sample. Typically, when that happens, you end up with bias in the estimator. Okay. What is going on in number 5? Take a random sample of 5 science and engineering departments, a random sample of 5 humanities professional departments. For each of the departments that we get, we list all the classes and we average those sizes. So first of all, what kind of sample is this? So we're starting by dividing the university or the courses into 2 kinds, right? Engineering versus other stuff, right? So that's 2 strata, yes? Within the stratum, we're then taking a random sample of 5 departments, and what are we doing with that? We're going to take every course in each of those 5 departments. So if we take a department, we've in effect taken a cluster of courses. We've taken all the courses that department offers. So this is a stratified cluster sample. Right? 2 strata, draw 5 clusters from each stratum. Right? Are all the courses equally likely to be listed? let's suppose that, oh, all right, so, I mean, the answer is no, but let's figure out how we could fix it so that it would be true. Suppose that there were 10 science and engineering departments and 10 humanities and professional departments. Then I would be taking 5 from each, right? The chance that I pick any given department would be the same, right? 50% chance that I get any particular science department, 50% chance I get any particular humanities department, right? If I do get that department, I get all the courses taught in that department. That make sense? So the chance that a course gets selected is the chance that its department gets selected, because if the department gets selected, the course does, okay? The chance the department gets selected would be the same for every department if there were an equal number of departments like this and departments like that. All right? So the reason that this doesn't give you the same probability of selecting every course is that you don't have the same probability of selecting every department. You would if there happened to be the same number of science and engineering departments as there are humanities and professional departments. Without knowing that that's true, if that isn't true, then this doesn't give equal probability of selecting every course. Does that work for everybody? All right. Okay. This one, random sample of 5 departments of one kind, 5 departments of another kind, then a random sample of instructors, and then you average the sizes of the courses those instructors are teaching. Now what do we have? We still have strata. Yep. But now, what's the next thing? Okay. Ultimately, we're pulling instructors. Instructors could teach 1 or more classes, right? So what we're pulling at the bottom is a cluster. So we have strata and we have clusters, but we have something else in between. It's a second stage, right? So this is a stratified multi-stage cluster sample. Yep. You're taking a sample of size 5, but it's not a cluster of 5 courses. It's not like I've divided the courses that the department teaches. So if the course, let's say the department teaches 30 classes, and I could do something where I have, okay, the first 5, the second 5, the third 5, on up to the 6th 5, right? And if my strategy was that I'm going to roll a die. If the die lands 1, I take the first 5. If the die lands 2, I take the second 5. That would be a cluster sample. But that's not what's going on here. You're taking a simple random sample of 5 classes from that department, if you get the department. Okay, sorry, that's from every department. So what you're ultimately sampling is 5 individual classes from the department, not one of a number of pre-specified sets of 5. Okay. Okay. All right, so this is a stratified multi-stage cluster sample. Right? The extra stage is, having picked a department, you then pick instructors from the department. And then the instructors that you just get all the courses that they're teaching. Pick a random number between 1 and 10. Starting with that class in the course schedule, you average the size of every 10th. You take every 10th class, you average the sizes. So this is just a canonical systematic random sample. It's systematic because you're taking every kth item. It's random because you're starting in a random place. Okay. Is every class equally likely to be in the sample? Okay, yeah, assuming it's a multiple of 10, that in all, every class is equally likely, but not every one of the number of classes choose whatever is equally likely, right? Because some subsets are impossible. Okay. All right. Okay, in the examples we've been talking about so far, there sort of really is a population. There's a population of courses, and they have a certain number of students enrolled, and it makes sense to talk about the average number of students enrolled in those courses. Or there's a population of women, and some of them have had extramarital affairs, and there really is a number that have had extramarital affairs, and we're trying to estimate that. There are a number of situations where it's useful to think about drawing samples from populations that don't actually exist. And we'll talk about a couple of examples of that. So first one is, suppose I want to know what the average test score would be for some group of students. And I'm going to do that by taking a random sample of students and administering the test to them. Okay? Use that to estimate. What am I estimating? Well, I'm not estimating the test scores of all the students because not all the students have test scores because not all the students took the test, right? I'm thinking about a hypothetical population of what would the test scores have been had all the students taken the test, but in fact they did not. Okay? So I'm thinking about drawing a random sample from a hypothetical population that doesn't exist because I didn't do the work, right? Okay. Now, that's one direction. Something that happens even more often is when you start thinking about the effect of a treatment. When you're trying to look at, I give some people a drug, I want to know what's the effect of this drug. And typically what I want to know is the difference between how many people would have gotten better if everybody had gotten the drug. How many people would have gotten better if nobody had gotten the drug? Okay. The example I've got written down here is like SAT training, SAT coaching, right? You coach some students. You want to show that SAT coaching works, right? I work for an SAT coaching company. I want to show that I have this great service and that I'm going to improve your SAT scores by 75 points. Okay? So how do I do that? Well, I would start with some collection of students. I would take a random sample of them. I would coach some of them. I would not coach the others. And I would compare the average test scores when we were done. Okay? That would be a reasonable thing to do. Okay? How do I know what the effect was on any particular student? I have no way of knowing, right? Because I can't simultaneously coach you and not coach you. So I can't compare your score with coaching to your score without coaching. Yes? Somehow what I'm thinking about is what would the average score have been had everybody been coached? And what would the average score have been had nobody been coached? And I'm trying to figure out what the difference is between those two averages. But that's the difference between the average of two lists, neither of which exists. Because any given student either was or wasn't coached. You don't get a list of numbers that has that student's test score if they were coached and that student's test score if they were not coached. You don't get both, right? Okay, so there's a hypothetical counterfactual. Yep.
Can they take the test and then coach them and take it again?
You can. The problem with taking the test, coaching, taking it again, is that there's actually some learning associated with taking the test. You have more practice taking that kind of test. You're also 3 months older. Other stuff. It's just hard to tease it apart. So, okay. So this notion of hypothetical counterfactual sampling from hypothetical populations is really useful. One of the ways people think about this, which we'll talk about a little later when we get into the analysis of experiments, is that every student is represented by a ticket, and that ticket has two numbers on it. One number is what would that student's score be if the student were coached? The other is what would that student's score be if the student weren't coached? And then we can think about, well, is there any difference between those two numbers? And one way to formulate things is if coaching makes no difference whatsoever, then for each student, the first number and the second number are equal. My number might not be the same as your number, but my left number and my right number are the same. Your left number and your right number are the same. Right? So if coaching makes no difference whatsoever, that's a good model of what's going on. Okay. Questions about this? do this example. Okay, so here's a city. It has 800 blocks. Blocks have an average of 50 dwelling units. Dwelling units have an average of 3 people, but not all blocks have the same number of dwelling units. Not all dwelling units have the same number of people. Every block has at least 10 dwelling units. There's no homeless people. Must be Southern California. Multi-stage cluster sample of city residents is drawn as follows. You pick 80 blocks at random for each block. You pick 10 dwellings at random, and the people in those dwellings comprise the sample. Okay, so you've got a random number of people when you're done. And one question is, does every resident have the same chance of being in the sample? How do you end up in the sample? Okay, so if your dwelling gets picked, you end up in the sample. For your dwelling to get picked, your block has to get picked. Okay. Every block has the same chance of being drawn. Every dwelling in a given block has the same chance of being drawn. But does every dwelling have the same chance of being drawn? No. Okay, if you're in a block that has a lot of dwellings, the dwellings in that block are less likely to get selected. The sampling fraction is smaller, right? Okay, it's the same thing we were talking about for departments over there. If every block had the same number of dwelling units, then every person would have the same chance of being in the sample, because you get sampled if your dwelling gets sampled, right? Okay. But because the number of dwelling units isn't the same in every block, the individual's chance of being in the sample isn't the same. It doesn't matter that there are different number of people in each dwelling, right? Because you get selected if your dwelling gets selected. So if the dwellings had the same chance of being selected, the people would have the same chance of getting selected. But they don't. Okay? So what kind of sample is this? Sorry? Multi-stage cluster. Yeah, this probably says that, doesn't it? Yeah. Okay. Wow, I'm consistent every once in a while. How about that? Okay. All right. So if you took the average number of people per dwelling in the sample, is the expected value of that average equal to the average number of people in the dwelling overall? The answer is not necessarily, right? Where would you have a problem in particular? Suppose that, sorry?
Some of the blocks might have houses with 5, 6, 7 people in them. Some of the apartments might have.
Okay, so it could happen that you have blocks that have sort of a small number of dwelling units with a small number of people in them. Okay, that would be like single-family dwellings versus tenements or something like that, right? If you have high density and a large number of people per dwelling combined, then the estimate is going to tend to be biased downwards, right? Because you have a smaller chance of selecting those dwelling units where the dwelling units have more people in them, okay? In the other direction, if you're out in some suburban area where there's, families of 4, 5, 6 people, and only 10 houses per block versus 150, dwellings in an apartment complex. Okay, then it's going to. Okay, so you get the idea that could introduce bias. Other questions? Yes. It's not stratified if you like divided the city into quadrants, like north, south, east, west, and then you said, from this quadrant, I'm going to draw 30 blocks from this quadrant, but instead you're drawing blocks from the city as a whole. So it's multi-stage because first you draw a block and then you draw a dwelling, but it's not stratified because you're not sort of dividing the city into groups of blocks and then drawing separately from each of them. Okay. All right. I'm going to take just like 2 minutes to tell you a little bit more about the election auditing I was doing yesterday. So the method for drawing the sample is actually a weighted random sample where the probability, so what I did was there were two experiments. One was looking at measure P in Davis, which there were 31 precincts that voted in the contest, and I counted by hand the number of votes that were cast in 6 precincts drawn at random from those 31. Actually, it was the 31 doubled into 62 because there were votes cast by mail and votes cast in person. But the goal of this auditing is to figure out whether there was enough error in the counting of the votes to cause the outcome to change. So if you're doing something like that, it makes sense to focus your attention where the errors might be biggest. So instead of drawing precincts with the same probability, I drew precincts that could hold more error with larger probability than precincts that could hold less error. Right? This is something that comes up in financial auditing a lot. Suppose that I've got there's a ledger with a bunch of, how many have taken some accounting classes or, okay, some of you at least. All right, so you got a ledger, you have a bunch of line items in the ledger. They have a book value, right? That's what it's reported to be, according to the book. And there's an issue of, well, was that let's suppose that this is a list of assets, okay? There's an issue that you might want to audit for is to determine whether the actual value of that set of assets is very different from the listed value of that set of assets, the book value of that set of assets. Have the book value been overstated, right? Well, if you're trying to figure out how much stuff has been overstated, it makes sense to look at the biggest items preferentially because they could have the biggest overstatements. An item that's listed for $1 could have been overstated by at most $1. An item that's listed for $1 million might have been overstated by $1 million. And so if you want to figure out if there's a lot of overstatement at all, you want to pay a lot more attention to the $1 million items than to the $1 items. So you're going to take a probability sample, but instead of taking them with equal chance of selecting every item, you take them in a way that it's 1,000,000 times more likely to select the $1 million item than to select the $1 item. And that lets you end up doing something much, much, much more efficient. So that's the strategy that we use in the election audit, and the difference was between looking at something like 6 precincts and probably looking at something like 30 in order to be able to conclude that if there were no errors, there wasn't enough in the sample, then that would be very unlikely to happen if there were enough error in the aggregate in the whole population of votes to have changed the outcome. So that was one thing. The other pilot was to pull individual ballots at random and look at the machine interpretation of those ballots and make sure that a human interpretation of the ballot matched the machine interpretation of the ballot. And that let us audit another contest in Davis, which was a vote for it wasn't in Davis, it was in Yolo County, vote for 2 of 4 candidates. And the margin between the second place and the third place, which is the margin between the last winner and the first loser, was only 16 votes. So it was a relatively narrow contest, but only spanned one precinct. And again, the idea is you're trying to come to a conclusion that if the outcome were wrong, you'd be very likely to see more error than you in fact saw in the sample. So if you see very little error in the sample, you can conclude with high confidence, small p-value, we'll get to all this stuff later, that the outcome of the contest is correct. Okay, I'll let you guys go. Have a good weekend.